Okay, let's get started. So we have worked very hard to set up the formal definition of limits and continuity using collapsing collections. And this is often the case with math where if you have a concept, then defining it rigorously can take a lot of work. And a lot of times those definitions are cumbersome to work with in practice. And so sort of the next step is that you want to develop tools that will make things easier to work with. And that's what we're going to do today. So like all of the conceptual stuff that we've been building up is now going to pay off and help us create tools that will make it easy to calculate limits and determine when functions are continuous. And this is the point in this course where we're switching from the little book of limits and continuity over to Stewart. So the content there is like a little bit of overlap. So right now we're in chapter 5 of the little book, and that overlaps with 1.6 in Stewart. So that's sort of where the stuff from today's lecture is coming from. But then after that, everything's going to switch over to being from Stewart. Okay, so let me give you the first tool. So this is a theorem. And this is going to tell you if you know a continuous function or two continuous functions, how to make more continuous functions out of them using the operations of addition, subtraction, multiplication, and so on. And I'm going to state the version for continuity right now, and then I'll also state the version for limits because they're related. So I'm going to suppose f and g are continuous at some value x equals a. And I'm going to also let c be some constant real number. Okay, so then here's what the theorem says. So the first thing is that, so this is going to say something about the sum of f and g. So f plus g is continuous at x equals a. So let's just think about this for a second. So if I have two functions, f and g, then there's another function called f plus g, which when I stick in a value like a, all it does is compute f of a, compute g of a, and add them together. So that's what that function is. And that will be continuous as long as f and g are continuous. And same thing for f minus g. And then we also have a product version. So the function f times g, not to be confused with f compose g, which we'll get to later, but f times g is also continuous at x equals a. And then we have a constant multiples as well. Which says that c times f, so if I take that constant and multiply that by f, that's also continuous at x equals a. And there's a quotient rule as well. So f divided by g is continuous as long as we just want that g is not equal to 0 at a. Okay, so this is a bunch of rules that tell you how to cook up new continuous functions. So, maybe I will let's just do a quick example to see like, how is this making our lives easier? So let's show that the function 3 times x squared plus 1 is continuous everywhere. Actually, are there questions about the statement of the theorem before I do the example? Yeah.
It's been a while. Do this, what is a theorem, sort of in the hierarchy of mathematical proof? Is that like a obvious thing, or thing that you have to prove?
Oh yeah. So okay, yeah. There's like all these different names for statements, right? So you have like proposition, lemma, theorem, corollary. Theorems are like the big ones. This could be like a theorem or a proposition. I think it's just a matter of taste, like what you want to call a given thing. But
what does it mean? Is it like it's obvious, or it's like you have to
it means like you need to prove, yeah.
Okay.
We need to prove something. So okay, yeah. So I'll prove this one, constant multiple, and the other ones are in the book if you want to read them as well. But just for sake of time, we'll just prove one of them. Yeah. But yeah, theorem is like a statement that you would want to prove or give some justification for. Yeah. Are there other questions? Okay, so let's do the example. So we know that the function x is continuous everywhere, right? So we know f of x equals x is continuous everywhere. So what I'm going to do is combine these using this knowledge in order to show that this new function is continuous. And I'm going to completely avoid collapsing collections with this. So from this, using the product rule, so by products, we then know that x squared is continuous everywhere. And then by constant multiples, I can also say three times x squared is continuous everywhere. Okay, and now I need to add 1 to this. And do we believe that constant functions are continuous everywhere? You can kind of imagine like what would happen. So if you plug in a collapsing collection, the image is only going to contain that one constant, and the wrapper will then only contain that one constant. And so that is a collapsing collection, just in a very trivial way for just that one number. So we can see that the constant function 1 is continuous. So then finally, by the sum rule, we get that 3x squared plus 1 is continuous everywhere. Okay, does this make sense? I think this should make us very happy, right? Because if we had to plug in collapsing collections into this thing, it could be kind of an annoying calculation, but now we can just run through these steps to build continuous functions, like complicated continuous functions out of like simple ones that we know, like x and constants. So let's make the following observation. So this, like, sort of by this calculation, I think you could convince yourself that all polynomial functions are continuous, just by a similar procedure. Do you believe this? So if you had some wacky polynomial function like 7x to the 5th minus 28x cubed plus pi x minus 6, something like that. All we would need to do to show this is continuous is break it up into small pieces. We would just have to, use the product rule 5 times to show that x to the 5th is continuous. Multiply that by the constant 7, and then we get that this piece is continuous. And we just move down the line and keep adding on terms. Does that make sense? Okay, so let's prove one part of the theorem. So we'll prove the constant multiple rule. And in the little book of limits and continuity, chapter 5, you can find the other proofs if you're interested to see like how the sum and the product rule are proved. Okay, so let's do proof of constant multiple rule. Okay, so let's let C be just some real number, a constant, and suppose F is continuous at x equals A. Okay, so what I want to show is that C times F is also continuous at x equals A. So I will have to use Clausian collections for this proof. So what we're going to do is pick a Clausian collection, plug it in to the function C times F, take the wrappers and hope to see that what we get out of it is also a Clausian collection. Okay, so I'm gonna take the collapsing collection okay, so what I'm gonna do for this is I'm gonna modify the standard collapsing collection, and we'll see why in a moment. So the standard collapsing collection for A would be A minus 1, comma, A plus 1, A minus 1/2, comma, A plus 1/2, A minus 1/3, comma, A plus 1/3. But I think I'm just going to stick with the standard collapsing collection. Okay, so we'll do this and we'll just plug this into C times F. So the next step is that we need to take images of this function, C times F, that we want to show is continuous. So we know, so what do we know? We know that if we plug the collapsing collection just into F, that we get a collapsing collection for A. Right? So, or sorry, for the value f of A. So what do we know? So if I take the wrappers of f of these intervals, this is a collapsing collection for the value f of A. Right? And this is because f is continuous. So let's think about what happens when I plug in an interval into C times f of A. Right, so if I know what f of this interval is, then what I'm gonna do is take all of those outputs and multiply them by C. Right, so whatever is it here, right, in this f image, everything is then just gonna get multiplied by C. So then if I take the wrapper of that, then that's gonna be the same as taking this wrapper and multiplying that by C. We agree with that? So what do we get out of this? So the F images, or sorry, the C times F images of our collapsing collection are C times these wrappers, F of A minus 1, A plus 1, F of A minus 1/2, A plus 1/2, sorry, C times that, C times the wrapper of F of A minus 1/3, comma, A plus 1/3, and so on. Okay, so we have something that is a collapsing collection, and then we're multiplying all of the values in that collapsing collection by some constant C. Is the new thing a collapsing collection? You were nodding your head. Why do you think it's a collapsing collection?
Well, it seems like multiplying it by C would not cause the conditions to qualify something.
Yeah. Yeah, so let's say, so we already know that, this set contains this set, contains the next set, and so on. So if I scale all of them, like, let's say I just double all of the intervals or something, that's not gonna change whether or not that containment is satisfied, right? And additionally, we know that at most one number is contained in all of those intervals. And so we're not going to pick up any new numbers by just scaling by C. Okay, so. And this is also a collapsing collection.
All right, and the last thing is
Yeah.
first, like, I guess, yeah, what do you mean by net numbers? It seems like there would be some, or they're probably, like, if you just go from, like, you just double the content, right? Like the new point that it's converting or not is, right?
Right, okay, yeah, so let's suppose, we had some number that was contained in all of these intervals. Then that number divided by C would be contained in all of those intervals. So the only option that that number could be is f of a. Maybe, yeah, I'll write that, I think that. Okay, so let's argue like why is there. So why is there only one number? Or let's say at most one number in all of them. So let's suppose like B is in all of these. Then that number divided by C will also be in all of the in all of these intervals, right? So then B divided by C is contained in the wrappers of the F images, which we knew to be a collapsing collection. So the only possible value for this is f of a. Which implies that B is equal to C times f of a. Oops, I'm running out of room. Then we can say, so this is a collapsing collection for C times f of a. Okay, does that make sense? We buy this proof? So that is the argument for why constant multiples are also continuous functions. And there's similar arguments for why adding functions and multiplying functions will also preserve continuity. Okay, let me do. So I said that there was going to be a limits version of this theorem. So let me write that down and do some examples with that. So here's the theorem. Limit version. So let's let f and g be functions. And let's also suppose that the limit as x approaches a of f of x and the limit as x approaches a of g of x exist. So these are just some real numbers. Then here's what we can say. So we can take the limit as x approaches a of, I'm going to put parentheses just to make it clear what I'm taking the limit of. So if I take the function f plus g of x, which is just f of x plus g of x, this is going to equal, if I just take the limits individually and add them. Let me put parentheses here. Okay, so it's like a sum rule for limits. And then sort of paralleling the continuity theorem we just had, we'll get products, constant multiples, and quotients as well. So if I take the limit as x approaches a of f of x times g of x, this is the same as computing them individually, so taking limit as x approaches a f of x and multiplying that by limit x approaches a g of x. So wait, let me. This is sums, products, and then constant multiples. So the limit as x approaches a of a constant times f of x is the same as pulling out the constant times the limit of as x approaches a of f of x. And then we also have a quotient rule. So the limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a f of x divided by limit as x approaches a g of x, just provided that this is not equal to 0. If this is equal to 0, then some wacky stuff can happen, and it really just depends upon the relationship between f and g, and we'll see how to figure out what happens when when the limit as x approaches a of g of x is 0. Okay, are there questions about this before we do an example? So I think this looks like a huge wall of formulas, but I think the way that you can interpret this is just that limits behave nicely with respect to addition and multiplication. So you can just break things up exactly as you would, as you might want to. Yeah. Just with respect to like the standard, you know, operations of arithmetic. Okay, let's do an example then. Let's take our removable discontinuity function and the jump discontinuity function. So r of x is 2x when x is not equal to 3, and it's 9 when x is equal to 3. And we'll take j of x to be 2x when x is less than 3, and 2x plus 2 when x is greater than or equal to 3. And let's compute some limits. So let's compute the limit as x approaches 3 from the left. So yeah, this theorem works also with left and right hand limits placed in there. So let's compute the limit as x approaches 3 from the left of r of x times j of x. Okay, so if you actually wanted to write down what the function r of x times j of x was, it would be a little bit complicated because we're dealing with piecewise functions, and so you have to be really careful with the different cases, like you go through and multiply them, how you would define this thing. But we can actually just ignore that for the purposes of this computation because we have these nice rules. So I know because of the rules that I can break this up into the limit as x approaches 3 from the left, r of x, and just multiply that by the limit as x approaches 3 from the left j of x. Okay, and we had previously computed these two things. So the limit as x approaches 3 from the left of r of x, just to recap. So we're always plugging in values where x is not equal to 3. So we'll just be getting closer and closer to whatever happens in this case when I actually plug in x equals 3. So this will be 6. And for this one, we're also still just plugging in values of x less than 3 of this. And so we'll also get 6 there. So in total, we get 36. And this sort of step, if you wanted to write a justification for this, you could say like by the product rule for limits. Are there questions about this? Okay, I want to give you another, so I'll say like how composition works with this now, and then we'll do a lot more practice. There's, in the web work, there's like a ton of practice with calculating limits. And the reason for that is because you're gonna want to get just very fluent in these like these types of calculations. So just like applying rules and breaking up functions to calculate these limits. Okay, so let's do composition. So we'll have a theorem. And I'll say the continuity version and then the limit version. So this says, let's suppose f and g are continuous. Then f composed with g of x, which just as a reminder is just f of, you plug in g of x, is also continuous. Let's prove this because it's gonna be really easy, actually. So I'm gonna start with a collapsing collection for some value. So let's let C1, C2, C3, and so on be a collapsing collection for x equals a. Okay, then since g is a continuous function, the wrappers of the f images of this are also a collapsing collection. Let's rewrite this. So the wrappers of the G images are a collapsing collection for the value G of A. Okay, so, so now these are a collapsing collection. So I wanna go ahead and plug those into F. And then we'll use the fact that F is continuous to conclude that what we get out of that is also a collapsing collection. One kind of fine point here is that these are all closed intervals, and technically when for continuity, we're supposed to plug in an open interval. So, what I'll do is, let's just, for these, we'll take the corresponding open interval, right? So a wrapper is one closed interval, so just change all of the closed parentheses to open parentheses. So I'm gonna okay, so I'll just denote that by like putting a little circle at the top. So this is like the open wrapper. Okay, so then if I plug those, so those are a collapsing collection still. So I'll plug those into F. So since F is continuous, I also get that the wrappers of the F images of these things so this is also going to be a collapsing collection, just by definition of continuity. For the value F of G of A. And this is really the same thing as if I just computed the F composed with G wrappers of my original collapsing collection. So this is the same as so that means that F composed with G is continuous. Okay, are we happy with this? Are there questions? Yeah.
Yeah, I guess one question I had is why do you need to go to this level of complexity? If you have, like, if you have this premise that be continuous just means to be within this property of continuity, like for all real numbers, and you know the output of G is going to be a real number, reals to reals, then you're basically just asking a question about plugging a real number into F, right?
Mm-hmm.
So like, why do you, what's the function of the field of collapsing?
Hmm. So let me think about this. So for example, like sine of 1 over x is not continuous at x equals 0, which like I think is fine because 1 over x is also not continuous at x equals 0. And that's like a composition of two functions. But I think maybe that example makes it clear that it's not completely obvious that that, you know, by composing functions, you would necessarily preserve continuity. I don't know, so. Like, like, sort of my view on like collapsing collections is like the moral of the story is like, if I zoom in on something or if I like stretch out, a particular interval, then that's not really like disturbing the function too much. And so you can think of like a composition of functions as like, so the function g is going to stretch or do something to the first set of real numbers that you put in, and then you're going to take those and plug them into f. And so it does sort of make sense that it would stay, that it would preserve continuity. Yeah. But yeah, this is just like, how do you prove it using collapsing collections? Okay, let me just write down the limit version. So this is like same thing, but limit version. So the limit as x approaches a of a composition f composed with g of x. So you have to think about this, like what's happening. X is approaching a, we're plugging that into g. And then whatever the output of that limit is, that's what we're putting into f. Right, so what this turns into is that this is the limit as x approaches L of f of x, where L is equal to the limit as x approaches A of g of x. So, for example, let's do the following example. So let's do L of x is equal to 2x, and we'll do the removable discontinuity function. R of x is 2x when x is not equal to 3, and it is 9 when x is equal to 3. So let's do the limit as x approaches 3 of L composed with R of x. Okay, so by the rule, this is going to equal the limit as x approaches L of, so here I'm just pattern matching, like I need to keep the left-hand one, so we'll keep L of x here, where L is equal to the limit as x approaches 3 of the right-hand function, R of x. Okay, so we know this limit, right? What is this? Yeah, it's a 6. Yeah, so okay, we'll actually, this is great. In 1 second, we'll get a really good rule for dealing with this type of thing. So yeah, right now, like we know how to say a lot of things are continuous automatically, and then we also know how to take limits of continuous functions, namely we just plug in the value. And we'll get sort of an analogous tool for this, like that'll basically say you can ignore the removable discontinuity and just plug into the like continuous piece of the function. Okay, so going back to this example, so we know this limit is 6. So now I'm doing down here the limit as x approaches 6 of L of x, and L is continuous, so this is just 12. All right, is this calculation okay? Okay, so now I'll get the rule that deals with R of X. And Dan calls this the switcheroo. Like it's a fancy name. So basically this is gonna say if F is okay, so I'll just write this down. So let's let F of X be a function. And let's let G of X be defined in a piecewise way to be equal to F of X for all but one value. And otherwise it's equal to like literally any number. So I'll just put like C for X is equal to A, where C equals anything. What this says is that the limit as X approaches A of G of X and F of X are gonna equal each other. I think this sort of fits with our intuition because basically, like to draw a picture of this, you have like some, so often it will be the case that the function that we replace G with is a continuous one. So maybe our function F looks, something like this, it's continuous. And then G of X agrees with F everywhere, except for in one spot where it has some other value. All this is saying is that the limit here agrees for both functions. This is A. Does that make sense? So this trick comes up all the time. And it's because, so on Monday, we'll define the derivative, and the derivative will be a rational function where the denominator is 0 sometimes, and so you get a little hole, but you can always do the switcheroo to replace this like function that is not defined at x equals 0 with a function that is defined at x equals 0, and then just plug in. So let's do an example. Let's just do the removable discontinuity example just to see how this works. And on Monday, we'll do like examples that are similar in flavor to what the derivative would look like, and then we'll define the derivative. Okay, so let's compute the limit as x approaches 3 of R of X. Okay, so we've already done this, but let's just redo it now using the switcheroo. So what that rule says is that I can replace R of X with just the function 2x. So this limit equals the limit as x approaches 3 of 2x. Okay, note, like R of X and 2x are not the same function, right? But the limits will have the same value. That's what we're doing here. We're just switching out the functions. Okay, and then 2x is a continuous function because it's a polynomial, and so that means I can just plug in x equals 3. This is 2 times 3, which is 6. So let's justify these steps. So this was switcheroo. And then this was because polynomials are continuous all we need to do to compute the limit as x approaches 3 of 2x is plug in okay, so that is how you use the switcheroo. So on Monday, we'll do more examples with this, and then we will define the derivative. And I hope you all have a good weekend.
That's your work.